A word of forewarning. Chapter 8 tends to be one of the more difficult things that we do in second semester. So if you got an A game, my suggestion is to try to bring it here for the next week or two while we kind of slog our way through this thing. In particular, one of the things that tends to give students a lot of trouble is there's a lot of vocabulary and notation stuff going on in Chapter 8, especially early on, that if you don't kind of keep these things straight, make sure you know what symbols mean and what phrases mean and things, becomes a problem later on. So again, if you can give your best attention to what's going on and make sure you're doing a good job, that'll go a long way, especially in the back half where things get, like the calculations get complicated. Early on, here in the first two sections or three sections, all the calculations are pretty easy, but there's a lot of vocab and notation going on. In the second half, everything gets complicated, but there's not a lot of new vocab and notation. So just kind of giving you a heads up, right? It's nice to know that, like, oh, if this is hard, it's supposed to be harder. Like, oh, this seems like a lot of stuff, you know. But, you know, it helps to kind of know that going into for you guys, right? All right. The plan here for today is to do the first two sections in Chapter 8. So in the first section, we're just going to kind of define something called a vector. And really, for the first half of this chapter, we're going to be focusing mainly in 2 dimensions on vectors, but we'll extend that and look at some 3-dimensional cases here towards the end. Okay, so start with some definitions here. So we say a 2-dimensional vector is a quantity that has 2 parts. So those 2 parts are both real numbered. One is called the magnitude, and the other is called the direction. When we describe a vector quantity, we want to be careful that we're not confusing it with like a variable that represents a single number. Vector quantities represent 2 things, a magnitude and a direction. So typically what we do is if you're typing something, you'll use a boldface, or if you're writing it on a piece of paper or your notes like this, we put like a little vector hat on it, like a half arrow. Here today, we're going to start by talking about some different ways that we can represent a vector, and we'll spend a little bit of time talking about how we can kind of translate back and forth between those different representations. So the first representation we'll talk about is a drawing or a geometric representation. So a drawing of a vector is going to really contain 2 points. So 1 point at the beginning and 1 point at the end. Typically, we draw one end of our vector as a point. We call that end the tail. And then one point of the other end of our vector we draw with an arrowhead. We call that the head of the vector. In a drawing, the length of the vector represents the magnitude, and the direction of our vector, typically in this kind of case, we would describe as like a standard position angle. So we just kind of draw in an imaginary XY axis at the tail, and then would describe the direction with kind of our standard form angle like we did in the first semester. So really, all that you'd be given typically for a drawing is your set of ordered pairs for the tail and the head. Everybody cool? So just kind of talking about some different ways of drawing these things, or writing these things, I guess I should say. So another way we can represent a vector is just by giving you the magnitude and direction of something. So for example, back in semester 1, we might have talked about a plane that's flying 250 miles per hour with a bearing of, like 105 degrees or something. So in a context like this, the speed of our plane would represent the magnitude, and the bearing there would represent the direction. But you could just, in general, you could just state those things, right? But that's a situation where we're kind of already familiar with that. We did some navigation problems in first semester that we could have also treated as vector problems. And then the third way of representing a vector, we'll see a fourth later on, is in a component form. And really, when we say a component form, we really mean like the standard representation component form. So when we say that, what a component form looks like is we use like a wedged bracket, and then we write like an ordered pair of numbers. In a standard representation, we read the tail at the point 0, 0, and the head to be the point AB. So that's just kind of when we write a component form, and in this class we're really always going to just be talking about that standard representation component form, but we're just going to call it component form. But all that means is it's a vector whose tail is at the origin and the head of the vector is at the point AB. But we're going to use the wedge bracket to differentiate ourselves between a vector and a point, because it's very important you're keeping those things straight, right? Because both of them look like an ordered pair if you use the same, the same bracketing. Everybody feel cool on that? So a little bit of notation stuff. So the magnitude of vector v, we're going to write as with like the vertical bars around the vector v. Now, we're abusing the heck out of this vertical bars notation because I think it's now we now have 3 things that vertical bar representation could represent. So if you went back to like your Algebra 1 class, we used the vertical bars as an absolute value. In your Algebra 2 class, if you think real hard and pay good attention, you have noticed that we also use that vertical bars when dealing with matrices to describe a determinant. And now here we're talking about it also using these vertical bars to represent the magnitude of a vector. So what's inside of those vertical bars matters a lot, right? That's what's going to tell you what it is you're actually doing. So the vertical bars around a real number is absolute value. The vertical bars around a matrix is a determinant. The vertical bars around a vector is a magnitude. So making sure you really understand what those vertical bars are around is really important because that's telling you which operation are we really doing here. Does that make sense? again, I want to, these places where the notation kind of can be a little bit tricky, I want to make sure that we're, that I'm being as clear as I possibly can. So direction, there's no fancy notation here, but I would want to point out to you that, you know, if I have one vector that's pointed like this and another vector that's pointed like that, now I've tried to draw those so they looked parallel. Do they look parallel to you guys? Near enough to, we can imagine that they are. Those have opposite direction because the arrows are pointing in the opposite way, right? So that's all I want to say about that. It's just that the way the arrow is pointing matters, right? Those are not the same direction. Those are opposite directions. Even though like they're parallel, they're making the same angle with the horizontal if you ignore where the head of the vector is, but the head, where the head is matters, right? Okay. So let's talk now about converting between these different forms or representations. So first thing we'll talk about is going from the drawing to component form. So in the drawing we have the coordinates for the head and the tail. Even if you're just given the drawing, you could read, you know, the points for the head and the tail off of the picture, right? To get this to component form, what I want to do is I basically am going to just pick this up and translate it so that the tail is now at the origin, right? That's all we're doing. So to do that, you're just going to take the head and subtract the tail from it. Sometimes this is referred to as the head minus tail rule. HMT is head minus tail. But that's it. Essentially, by doing that, subtracting x1 from every x coordinate and y1 from every y coordinate, you've taken that entire piece and you've just translated it. So now it's starting at the origin. Notice that doing a translation, the length of your vector will not change. The direction of your vector will not change. Just the location of the vector has changed, right? It's just now located at the origin. But that's really easy to do. Everybody cool? Again, most of the calculations we're going to do today are going to be very simple. Just making sure we understand what they mean, and what does what can be the tricky part. Next thing we'll do is we're going to go from component form to a magnitude and direction. So the magnitude, we remember in the drawing form, is just talking about the length of something, right? So if I want to calculate the length of a segment in your geometry class, what would we have used? The distance formula, right? D is equal to the square root of x1 minus x2 squared plus y1 minus y2 squared. Now in component form, one point is AB and the other point is the origin. And in component form, the other point is always the origin. So this really just simplifies down to the magnitude being the square root of a squared plus b squared. Again, very easy calculation to do, right? You just plug two numbers into a formula and keep in mind that the square root of a squared plus b squared is not a plus b. Just as a reminder, we've hit that. I think I've made some other point of making sure that we mention that at other times, but I'll continue to do so as it's not an uncommon mistake. The direction now, let's say we have some vector here that's, if we want the direction, we're talking about the standard position angle is what we're looking for. And boy, howdy, this starts to look a lot like a first semester question. And in fact, I would do this the exact same way I did in first semester. So I'd think about the angle between the x-axis and my vector, in this case, really the same thing as your terminal side of an angle. Call that angle measure alpha. And then I have the other end of my x-axis. In this case, that would be at 180 degrees. So my angle theta in this case would be 180 minus alpha, where alpha is the tan inverse of the absolute value of y over x. Just like we did before, right? Which is lovely, right? I love when we recycle, you know, like a procedure that we had before into a new context, because it's nothing new to learn. It's just reusing stuff we've already developed. So remember that what we're adding or subtracting alpha from is always the angle measure on the x-axis that makes up the alpha. And then whether we use the addition or subtraction for alpha depends on which axis we had crossed previous. So in this case, since we're passing a vertical axis, we're subtracting. If you were crossing a horizontal axis, you would be adding. Just to remind you guys, again, we did this all first semester, but you know, it's been a bit. Cool here. Again, just reusing something we've done before. The next thing we'll do is going from component form to magnitude and direction. I'm sorry, we did that, that's what we just did. I wanted the other way. Magnitude and direction to component form. So let's say that we'll write the magnitude of V as using the vertical bars notation. And we'll just call theta the direction of V. So then in component form, our component form representation for V is going to be the magnitude of V times cosine theta, comma, the magnitude of V times sine theta. Does this look familiar? When we did those vector problems in first semester, this is what we were really doing when we were adding the vectors together. We broke it down into an x part and a y part, and then added the x parts and added the y parts. The way we broke it down into x and y parts was doing the magnitude times cosine theta and the y parts magnitude times sine theta. So again, something we've already kind of done before. We're just kind of formalizing it and using it in another place. But again, simple formula, right? Really easy formula to apply. And in fact, we've used it before, which is really nice. So I'm going to stop here in terms of ways to convert between the representations. The other two that we haven't done yet are going from a drawing to magnitude and direction. Why am I not going to bother with that? Because the way that I would do it is just convert it to component form and then do component form to magnitude and direction, right? So like it's going to be, that's actually the easier way to do it, is to do it that way as opposed to try to go directly from the drawing. So that would be my suggestion there. That's why we're not going to list that as a separate thing. And then the other piece that we're not going to list is going from component form to a drawing, because literally the definition of component form is the tails at the origin and the head is at the point AB. So like there's really nothing to say there. Is that okay? So I'm not going to bother writing down either of those two situations because they're kind of trivial, because one of them is just combine two of these methods, and the other one is it's the definition. And that, I think, covers all the different conversions between the three forms. Let's do a couple of numeric examples, right, just to make sure we got it. So let's say we have the vector xy, where x is the point 3, 2, y is the point 5, 1, and then we want the component form. So here I have a graphical representation or a geometric or a drawing or whatever you want to call it. So I know I'm just going to be using that head minus tail rule to do this. But which point is the head and which is the tail? Aiden?
Y would be the head and x would be the tail.
Yeah, how'd you know that?
Because the way it's drawn is x, y.
Yeah, so the arrow on top of the xy is telling us which point is the tail and which point is the head. Exactly right. So if the arrow is pointing the opposite direction, x would be the head and y would be the tail. Everybody cool? Again, very straightforward. But if you don't remember, easy place to kind of get tripped up. So here the component form is 2, 3. This time, let's say we have the vector u in component form, which is equal to negative 2, 5. And we want the magnitude and direction for that vector. Well, the magnitude is easy. Just the square root of a plus b, or square root of a squared plus b squared. So that's the square root of 29. That radical can't be reduced. If it could, you could go ahead and do that. Or depending on the directions, you could write it as a decimal. I'm just going to leave it the way it is for now. And then to get the direction, I'm going to plot the point negative 2, 5. And then I want this angle. This is my alpha. The other side of alpha, or the other arm of alpha, is the 180-degree side. So we have theta is 180 minus alpha, where alpha is the tan inverse of b, or I'm sorry, absolute value b over a. So I'll just go to my calculator to do that. Again, noting my calculator should be in degree mode. Almost always you'd represent your directions with angle measures as opposed to radians, or degrees as rather than radians. And notice that I didn't bother to do the absolute value in my calculator. I just did that part in my head because it was way less buttons. So I get 111.8. So magnitude, direction. my third direction, or third example here. We're given a magnitude of 5 and a direction of 224 degrees, and we want component form out of this. That's really easy. Magnitude times cosine of direction, comma, magnitude times sine of direction. Notice there I'm being very careful about my bracketing, that I'm making sure to use the wedged brackets here to represent my component form answer. So I get negative 3.6 comma negative 3.47. We feel okay here so far? Again, all the calculations are very, very simple, right? And just kind of keeping track of the vocabulary and the notation. Paul?
What's the difference between those brackets and like regular brackets or parentheses? No, I understand that, but like, what's like, is there a reason to use those?
So that you're not confused and think that A comma B is a set or a point. Is to make sure that we are able to tell that by looking at it that like, oh, we're talking about a vector in component form, right? Because there's lots of other things where you could have like, you know, like this would be a set of numbers. This would be an ordered pair. This is a vector. So you're able to just kind of look at the symbols and know what it is you're talking about. That's why we're using the wedge bracket there instead of anything else. Is that cool?
Yeah.
So it's because the other things are already being used and conceivably could be used in this kind of a context also, and it's just for clarity. So of these three representations, the two that we're going to be using the most are going to be component form and then the magnitude and direction. Not surprisingly, we don't want to rely on like constructing pictures in the XY plane and doing like, you know, pain in the tuchus geometry to figure things out. Now, for the most part, both component form and magnitude and direction have advantages and disadvantages. The main advantage of the magnitude and direction is that they have often a real meaning in the real world. So like the magnitude of something corresponded to like how fast the plane was flying or whatever when two vectors got interacted with each other, or, you know, the direction is like the bearing that you'd want to take to end up someplace when we did those, you know, like those have real world meanings. The advantage with the component form is the vector operations are really simple to do in component form. The algebra is really easy. So kind of a standard thing we would do with vectors is you take your magnitude and direction, convert it into component form, you do all the calculations in component form until you get your answer, and then convert that back out to magnitude and direction, which tends to be the simplest way to do things. So when we talk about vector operations here in 6.2, we're going to be talking about everything in terms of component forms because the calculations are really simple. Okay, so vector operations, we're going to start by defining a special vector called the zero vector. What letter do you think we're going to use to represent the zero vector? Not Z. We use O. Why O? It looks like a zero. Now, got to be real clear on your sheet of paper. The vector O and the number 0 do not mean the same thing. So you need to make sure that you're putting the vector hat, or if you're reading the notes, that the vector O is boldface as opposed to the number 0, which is regular typeface. So it's got to be a little bit careful. So this is a vector with magnitude 0. and no direction. This is the only vector that has no direction. And you're like, well, that seems kind of weird. I'm like, well, it's not that weird. If you think about 0 in the real number system, 0 is the only number in the real number system that doesn't have a multiplicative inverse, right? Typically, the way you find the multiplicative inverse is with the reciprocal. And obviously, we know the reciprocal of 0 is undefined. So no multiplicative inverse. It's just the way it is. So let's start with addition and subtraction of vectors. So if I have the vector u, that's component form u1, u2, and the vector v, component form v1, v2, and we'd say u plus v is going to be just u1 plus v1, u2 plus v2. Geometrically, what does that look like? So if I have the vector u, then I have the vector v. If I were to add those together, basically what I'm doing is I'm going to be placing the vector v at the end of vector u, and then u plus v would be the new component form vector to the from the origin to the end of v. Everybody okay with that idea? Again, the geometric piece, it's just for intuition, right? We're not going to actually ask you to do that kind of thing, but I think it helps intuitively to get an idea of like what it is that you're actually doing algebraically. Or at least it helps me. I'm a pictures guy. So looking at these two ways of thinking about it, either as a component form or as a geometric form, is addition of vectors commutative? Is u plus v the same as v plus u? Yeah, for sure, right? If u1, v1, u2, v2 are real numbers, then obviously those are commutative, so they're going to give you the same answer. Or if we drew our picture, if we had done, started with v and then drawn u, we'd still end up at the same spot, right? You'd have a different triangle that you drew, but still the same picture. And in fact, if you draw both of them like we did there, you end up with what shape? It's a parallelogram, right? You guys see that? Okay. Not surprisingly, vector subtraction works the same way. Now, we've done addition and subtraction of vectors. The next two operations you suspect we'd be talking about is multiplication, division, right? There is no multiplication of vectors. There's no division of vectors. Oh, okay. There is a type of multiplication. It's called scalar multiplication. But it's between a scalar, which is just a real number, and a vector. So k times the vector v just is k times v1 and then k times v2. Again, really intuitive, exactly like you'd hope it would, right? So what is scalar multiplication look like graphically? So if this is my vector v, if I wanted, say, 4v, that's what 4v looks like. Basically, 4 v's just stacked right on top of each other like that. Is that cool with you guys? So one thing we can note right away from the picture, the magnitude of 4v should definitely just be 4 times the magnitude of v, right? So you can pull those scalars out of magnitudes if you like. You don't have to, you could leave it in there, but that's certainly something that's true. I guess we could say that generally, right? Use k. But that can make calculations sometimes a little bit simpler. Okay. Next, we're going to observe another special vector called the unit vector. So we say that vector u is a unit vector if and only if its magnitude is 1. So how many unit vectors do you suppose we have? What do you guys think? 1? More than 1? Infinite is the answer, yeah. So what are they going to look like? Well, if you remember the unit circle, any point on the unit circle we could represent as cosine theta comma sine theta, right? Everybody agree with that? And the distance from that point back to the origin was 1, because that would be a radius of that unit circle, correct? So the component form, cosine theta comma sine theta, represents something that's a unit vector. And since there's infinitely many points on the unit circle, we have infinitely many unit vectors, right? Every unit vector could be represented in this form. So one of the really important pieces for unit vectors is they essentially capture the direction portion of your vector uniquely, right? That they don't have an impact on the magnitude, they just capture the direction piece. Cool with that? So one thing that we're going to be interested in is getting a unit vector in the same direction as a specific vector. So if I want a unit vector that's in the same direction as the vector v, well, what I'm going to do is I'm just going to take 1 over the magnitude of v and multiply that to v. Now remember, 1 over the magnitude of v is just a scalar, right? That's just a real number. So if I want to take the magnitude of u, I can pull that real number piece out. Where I just have now 1 over the magnitude of v times the magnitude of v. That's just 1. And since all we're doing is doing a scalar, we know that the direction of u hasn't, or the direction of v hasn't changed. by scalar multiplication, right? When we drew the picture, it was just stacking on top of one another. So definitely got it. So that's it. Easy peasy. Let's do a quick numeric example here. Let's say our vector v is 5, -6. And we want to find the unit vector in the same direction. So the first thing I'm going to do is I'm just going to calculate the magnitude for v. So 25 plus 36, that's 61. So 1 over the square root of 61 times the vector 5, -6. So I do my scalar multiplication. And then I'm going to rationalize my denominators. There's my answer. Note that we could check that if we wanted by calculating the magnitude for this. So let me do that real quick here just to show you guys that what we have is indeed a unit vector. And when I do the magnitude on my calculator, I get 1. Everybody feel pretty convinced? Okay. There are 2 unit vectors that are of special importance. They're called the standard unit vectors. So the first one is called I, and it's equal to the vector 0, 1. And the second one is j, which is equal to the vector, I say that backwards. I is 1, 0, j is 0, 1. Excuse me. I think I reversed that. With these 2 standard unit vectors, we can unlock a new representation. This is called the linear combination representation. So if I have some vector v, it's equal to the component form CD. I can rewrite this as the sum of the vectors I and j in the following way. So CD I can think of as C0 plus 0D. Everybody feel okay with that? And C0, well, that could just be C times 1, 0. And 0D could be D times 0, 1. And 1, 0 is just I. And 0, 1 is j. So there's my linear combination representation. Basically, all I'm doing is taking the c, the x component, slapping an I on it, and taking the y component and slapping a j on the end of it. Again, very, very simple. You just have to remember, like, what the heck is a linear combination representation, right? That's the hard part, is just remembering all the names of stuff. But the actual thing you're doing is very, very simple there, right? Okay. One more operation to talk about called the dot product. So if we have vectors u and v, we say that u dot v is equal to u1 times v1 plus u2 times v2. Notice something unusual about this dot product? If I look at the definition, the items on the left are both vectors. Everything on the right is scalar. So the dot product of two vectors is just a number. It is not another vector. We'll do a couple of numeric examples here in a second. Before we do that, though, let's look at a couple of properties for dot products. So the first is the commutative property. And it just says that you can do the dot product in any order. That u dot v is the same as v dot u. The next is the multiplicative identity property that says the zero vector dot any vector is just equal to 0. The next is the distributive property. It says u dot the quantity v plus w is equal to u dot v plus u dot w. And the order that you do that, whether you're doing the dot product from the left or the right, doesn't matter. Scroll that up for you. Next is the scalar associative property. It says the scalar times the dot product of uv is the same thing as the scalar times the dot product u, or sorry, scalar times u and then dot v, which is the same thing as u dot the scalar times v. So basically we're saying it doesn't matter when you do the scalar multiplication. You can do it after you've done the dot product, before you've done the dot product, and to either of the vectors involved in the dot product. It doesn't matter when you do that scalar multiplication. And then the last one is the magnitude property that says that u dot u is going to equal the magnitude of u squared. We're not going to prove any of these properties here in class because that's actually part of your problem set. None of the proofs are terribly difficult. They're all very realistic. In fact, some of them are almost trivially easy, like the multiplicative identity one is like real easy. I could. Let's do a couple of numeric examples here. So let's say u is the vector 2, -3. V is the vector -1, 5. W is the vector 8i plus 4j. And we're going to do u dot v, and then w dot v, and then 5w dot u, and then lastly u minus w dot 2v. God bless you. All right, first one, u dot v. Well, according to the dot product formula, that's just u1 times v1 plus u2 times v2. So I just get -17. Everybody cool with that? Nothing really tricky or difficult going on there. B, I have w dot v, and oh no, w's in that kooky linear combination form, but v is in that component form. What should I do? I'm just going to convert w into component form to make this easier. That's just going to be 8,4. Since the I is basically just the X component, the J is basically just the Y component. So that's easy enough to do. Okay, so I'm going to have W1 times V1 plus W2 times V2. Gives me -12. Yes, Jack. Yep. Thank you. Okay. The next one I have 5w dot u. According to that scalar associative property, I can kind of do that 5 whenever I want. That's the order that I'm going to choose to do it. So I'm going to have 5 times, and then w1 dot u1 plus w2 dot u2. And that just gives me 20. So far, so good. On D, I'm going to choose to do that and just do this as an order of operations problem. So U minus V gives me 2 minus -1, and then -3 minus 5, and then dot 2v is -2, 10. Then when I do my dot product, I have 3 times -2 plus -8 times 10. That gives me negative 86.
Look,
Yeah.
for D, is that U minus W or U minus?
Oh my goodness, did I do the wrong thing? Hold on, let's check here. I did U minus V. Boy, I'm dumb. Hold on, let's do a different color. Let's see, U minus W, U minus W. That's better. Thanks, Aiden. Oopsie-daisies, right? Okay. Again, none of these calculations are terribly difficult. You're just plugging stuff into formulas, right? You feel good? So far, so good? Okay. Just a couple things left to do. So next thing we're going to talk about is the angle between two vectors. So let's say we have the vectors u and v as I've drawn here. The angle between those two vectors is this angle here that we've drawn. So the way to find that is going to be the cosine theta is going to equal the dot product of u and v divided by the magnitude of u times v. Or if you just wanted theta in itself, you just do the cosine inverse or whatever. Now this is a deceptively confusing formula. In the numerator of that formula, what is that symbol in yellow? That's the dot product. In the denominator, what's the symbol in green? Multiplication. What? Mr. Kulik, it's the same symbol. Yeah, but in the numerator, it's between two vectors. In the denominator, it's between two scalars. Magnitudes are just real numbers. Very easy to kind of get turned around on that and forget which one is which. Again, got to be kind of paying attention and going, what kind of quantity is that symbol in between or is that symbol surrounding? Because we have both real number symbols going on and vector symbols going on, and they're sharing some of the same symbols, right? So you got to be a little bit cognizant of that. We're not going to prove this. The proof of this is ostensibly just using the law of cosines. If you wanted to take a look, it's in the lesson notes, but I'm going to skip it for now. So let's say that we wanted the angle between these two vectors, u and v. So to do this, I'm going to need the dot product of the two vectors. I'm going to need the magnitude of each vector. 42 plus 36 is 78. No. That's 49. Jeepers creepers, Mr. Gulick. Plus 36, so that's going to be 85, or square root 85, I guess I should say. And then square root of 2 squared plus 2 squared is square root 8. Notice that perhaps I could simplify these radicals. I mean, I can definitely simplify square root 8, but I don't care because those are not going to be in my final answer anywhere. So I'm not going to waste my time trying to simplify any of these radicals. I'm just going to leave them as radicals because they're just going to go in place of my formula. And that's what I'm typing into my calculator. So I'm not going to waste my time and effort to simplify those radicals when my calculator doesn't care if the radicals are simplified or not. And nobody needs to see that as part of my final answer, so I'm not going to do it. So I get 85.6 degrees when I type that in. Worth pointing out, since this angle between two vectors formula involves the cosine, or cosine inverse, I should say, we know that the range for cosine inverse is 0 to 180 degrees. So what that means is that we're always going to be finding the smaller angle between the two vectors. We would never be finding that piece. That's the bigger one. So keep in mind that even if you have like a vector here and a vector there, the angle you're finding is going to be this one. Or the formula is the angle the formula is going to give you is always going to be that one. It's always going to be the smaller one, not necessarily the like going from left to right. It's always going to just be the smaller of the two angles between the vectors, right? Now, I don't think that'll matter if all you're doing is pounding things through the formula. But if you're drawing a picture to be like, hey, does this angle even make sense? There's a place where you could get oops-a-daisied because you're like stuck looking for one that's bigger than 180 degrees and not getting an answer that's bigger than 180 degrees. The formula is always going to find that smaller angle. Okay, one last definition for today, and we're going to be donezos. Didn't that feel good? That definition is called orthogonal. So the vectors u and v are called orthogonal if and only if the dot product of u and v is 0. What's orthogonal mean? Well, really just means perpendicular in vector land. So it really means the angle between those two vectors is 90 degrees. So for example, we're asked to show that the vectors negative 5, 8 and positive 16, 10 are orthogonal. All we need to do is take their dot product and show that dot product simplifies down to 0. So I get negative 80 plus 80, which is 0. And I'm done. Very easy to do, right? Now you have to remember what orthogonal means, that it means the dot product is 0. But, you know, easy to do that if you remember the name or not remember the definition or whatever. The calculation is piece of cake. So far, so good? we're stopping here because, quite frankly, we just bulldozed through 2 sections and it's a Friday. So you guys should, at this point, be able to do 1 through 40. That's going to go into next week's problem set. Hey, and that's going to go into next week's problem set. So Sunday, this Sunday, is just the Chapter 7 review. Next Sunday, 1 through 40 is going to go in there, plus whatever we're going to get through next week. Now, keep in mind, the example things that we did, were any of them time-consuming? Not really. The calculations were like 30 seconds to do, right?
Just doing the right calculation.
It's doing the right calculation, which is the whole point of doing the practice, is just to make sure you get used to which one, what does what, or what means what.
Can I go to that?
Yeah.